This is a screencast of the MergeSort example that we did in class on Friday. We'll finish up the example here, and then we can move on. So why should we use MergeSort, and why should we look at it? Well, it's a great example of divide and conquer. It's better than the order n squared algorithms you can find. Its worst case performance is better than quicksort. It's really simple, easy to understand. It motivates the two guiding principles that we are going to spend a lot of time on this term, and that is worst case analysis and asymptotic analysis. And our methodology for its analysis will be something that will carry forward throughout the rest of the term. So here's MergeSort itself. Because it's a divide and conquer algorithm, the best implementation of it is recursive. And every recursive algorithm, of course, has to have two parts. The first part is the base case, and then the second part is the recursive cases. In terms of MergeSort, we set up the recursive cases by computing the sizes of the two halves of the algorithm, and then we sort the left half of the list, and then we sort the right half of the list, and then we merge the two sorted halves together. The merge is where most of the work gets done, and the merge is done by figuring out which element is the next one to put into the temporary array. We do that by having a loop that goes through each subarray and then looks for the smaller element and puts it into the temporary array. Then at the end we copy over what's left in one or the other of the two subarrays, and then we copy the whole temp back into the original list. So the running time of MergeSort. The metric we'll use is number of operations, or kind of to make it simpler, lines of code. We don't have to worry about the architecture of the machine that we're running on. So we'll just look at what a single merge does, and then later on we will work at doing the entire MergeSort. So for the merge, there are a number of things that we have to do. The first thing that we have to do is initialize the loop control variables, the indexes into the two subarrays that we're going to merge. That requires 4 operations, 3 for the indexes, and then 1 to compute the beginning place of the second array. We then enter a loop where we compare elements from each array and grab the smaller of the two to insert into the temp. The loop itself will count as 1 element. The if statement will also count as 1 operation. And then the results of the if, it's either 2 operations if we take the then clause, and that is that the element from the first list is smaller, or it's two operations from the second clause. Then the last thing that we do in the loop is we increment the counter for the temp array so that we know where we are there. Once we're finished with that, so what we get then for the array itself is 1, 2 plus 2 is 4 plus 1 is 5 operations for the loop that's doing the merge. If we assume that the number of times that we'll go through the loop is at most the sum of the 2 subarrays that we're doing, then we'll have a number that we'll call m, and that's going to be equal to n1 plus n2. And so the total number of times that we will go through the loop is 5m. Finally, once we finish the big loop, we have to copy the remaining elements from one or the other of the 2 subarrays, and this one will be at most m over 2. The second one will be at most m over 2. In reality, you're really going to just execute one of these, but the total between these two other loops here is only m. And then finally, we copy all of the elements from the temp back into the original array, and that's going to take an additional m elements. And so we get, at the end, we get 5m for the main loop plus 2m for the miscellaneous loops that where we have to copy things, plus the initial 4 operations. And so this we end up with is 7m plus 4 is the total number of operations that we get in the loop. Now, to simplify things, we'll say that that 7m plus 4 is less than or equal to 11m for all m greater than or equal to 1. Okay, and it's easy to figure that out, and it's easy to see that that is in fact true. And so, for MergeSort, we're going to claim, and so for MergeSort, we're going to have to start by looking at the algorithm itself and trying to figure it out. So to begin with, we claim that the running time of MergeSort is going to be less than or equal to 11n log to the base 2 of n plus 11n. And the question is, why is this good, and why is this a good way to do it? Well, let's stop here for a minute and go take a look at GNU plot, and then we'll come back and work on that. Okay, we're back. We claim that MergeSort requires less than or equal to 11n log to the base 2 of n plus 11n operations. So to prove this, what we have to do is look at the recursive tree for MergeSort. So if we start with a list that's this big, the first thing that has to happen with MergeSort is we divide the list in half. Right? And then we come down here and we sort this half, and we will eventually come over here and we'll sort this half, and then we'll sort this half, and we'll sort this half, and dot, 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 and eventually we get down to these arrays that are just one element long, and that's when we'll get to the base case of the MergeSort. Now, each one of these recursive breaking the problem in half is called a level, and we start with level 0, and so that means this is level 1, etc., going down, 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 down. And so what's the bottom level? The bottom level is what? Yes. It's log 2 of n. Okay? That gives us a total number of levels of log 2 of n plus 1. Okay? All right. So now, at each one of those levels, okay, there are 2 to the k subproblems. So the level 0, there's 1 subproblem. Level 2, there's 2 subproblems. Level 1, there's 2 subproblems. Level 2, there's 4 subproblems. And then each of those subproblems is of size n over 2 to the k. So for level 1, each problem size is n over 2. For level 2, there's 4 problems, and each one of them is n over 4, etc., etc. And so the total number of operations at a particular level is 2 to the k times 11 times n over 2 to the k, okay, where this is the number of subproblems and this is the number, the size of each subproblem, and the 11, of course, is the relative number of operations for each execution of the subproblem. And so this, it turns out, of course, is 2 to the k times 11n over 2 to the k, which is just going to be equal to 11n. And so at each level, the amount of work we do is actually independent of the level number. Okay, and so this means that the total number of operations is going to be 11n, which is the number of operations at each level, times the number of levels, which happens to be log 2 of n plus 1, and so that happens to be then 11 log 2 of n plus 11n, excuse me for my really horrible handwriting. And that's the claim. So we're done with the proof. Q, E, D. Okay, so what you see finally is the technique that we use is we develop the algorithm, and we'll come back to this later. We decide on what it is we'll measure. We were measuring operations, or really instructions. We identify the area where the algorithm is doing the most work. For MergeSort, it was the merge algorithm. You count the number of operations there, and then you develop a hypothesis on the complexity, and then you prove it. And that's sort of the technique that we'll be using for the rest of the term. So thanks for listening. See you later.